Hello everyone. Today we will start with the plastic analysis. Okay. So before we go into the plastic analysis, we need to understand what I mean by plastic analysis. For that, we need to look into what is elastic analysis. What we did in elastic analysis, and from that, after the elastic analysis, we start the plastic analysis. So we look into the basic concepts. Okay. So what we had here. Now, the elastic analysis, so the stress strain, the curve what we got. If we know this, now this is my stress and this is my strain axis and this is linear, okay, linear up to its yield stress, then it remain as an horizontal. Okay, so we know the understanding of this, what it says. Now up to, okay, up to the yield strain, up to the yield strain, the stress and strain will be proportional, that is linear, from the Hooke's law. And here, after the strain beyond this yield strain, this is my Fy and this is my yield strain. Once the strain increases beyond the yield strain, there will be no further increase in the stress, so it will just simply deform. Okay, my elastic analysis ends where any one of the fiber in the cross section reaches the yield strength. Okay, so that is my elastic. Now we have the Hooke's law. Now Hooke's law says what? Hooke's law, so that is stress is directly proportional to strain up to proportionality limit, right? So that's what. Now here proportionality limit and elastic limit and yield will be so close, so that's why this is the characteristic curve or the design curve what the IS code gives. Okay, so this is for the structural strength. Now if I take this beam, okay, the beam is loaded here and the bending moment shown here. This is where the maximum bending moment will happen. So that is will be PL by 4, okay, and this is the length of the span. Okay, now if the cross section of the member is rectangular, for example I'm taking a rectangular, it is B into D. Now the strain profile, it is going to look like this way. It's going to look this way. Now this is almost a straight line because that's what we have the assumption in the simple bending theory. Okay, now here, okay, let me write this again. So okay, I'm sorry. So if I take this and if I draw on this one, so assume that like this is almost a straight line. Okay, so almost a straight line. Now this is, and this is linear, and this is where my neutral axis comes. This is where my neutral axis comes here. This is my neutral axis. So, and it is a sagging bending moment, so I will take this as a compression and this area will be under tension. And here now, if this strain, this is the maximum strain, it happens, and if this if any of the one fiber, okay, any of the one fiber reaches the yield strength, that's where my elastic analysis ends. Okay, that's the where I am going to calculate my capacity. Now following the Hooke's law, okay, and my stress profile will also follows the same. Okay, so this is my Fy, and this is also here Fy. Okay, now this is the strain profile, strain, and this is the stress profile. Okay, so how do we calculate the moment capacity now? In elastic analysis, this is the point where we do the analysis. Now in elastic analysis, this is how we do it. Okay, that is right. So we have this simple bending equation, that is m by I is equals to F by Y is equals to E by R. I know, so you know all these meanings of these terms. So I want to calculate my elastic section capacity. So it comes Fy into I by Y. Okay, so this is Fy, or the stress at any particular fiber at a distance y from the neutral axis. Now here y, it is going to be y maximum. So this is what we called as elastic section modulus. So ME. Okay, so what this is, look at closely. If you have a section and if you know the section modulus for that section, and this is the allowable stress in the bending, okay, this is the allowable bending stress, then we can calculate my elastic section capacity. Okay, so this is what we used to calculate and how we used to do the design and all. Now here in the plastic analysis, what we are going to do now, in the plastic analysis, now, if you look at this curve, if the strain increases beyond the yield strain, the stress does not increases, it will remain constant. Okay, and because steel is a ductile material, you can rotate, or you can have very large strain before it actually fractures. This is the ultimate strain. Now taking this advantage of the ductility of the steel, okay, the question is what happens if I load further beyond my elastic capacity. Now if I am going to increase the loading, what happens? My strain in the profile, it is going to bend more, the beam is going to bend more. So because of the bending, how my strain here, so it increases. Okay, it increases. Now what happened here? Now before this was the yield strain, now this fiber is actually at a higher strain. Okay, it's actually at a higher strain. So, and also what happening in the elastic analysis, in the elastic state, the fibers here were actually less strained than the yield strain. Now if we are increasing the loading here, so these layers are actually straining more, right? So the strain are actually yielding now, though the strain here is more than now yield strain. So that's what we call like these fibers are now yielding. Now here what happens here, up to here, now this is, I'm taking this an instance, so up to here the strain is actually more than epsilon y, here it is actually less than epsilon y. Okay, for this case, if I write the my strain profile, this is how it's going to look like. Up to here it is actually the strain here. Okay, now up to here This is the strength. Okay, so Fy, and this is Fy. Now all these fibers have having a strain more than yield strain, and these fibers up to this particular point, okay, between here, this is having lesser stress and lesser strain than the yield strain. Now if this is how it happens, and then if you further load, if you further increase it, what happens? The strain here, okay, it increases, okay, it increases here, it increases to a very high. That is all the fiber in the section, they have been yielded. That is, the strain in all the layers in the section is more than my yield strain. For that case, if I write my strain stress profile, this is how it's going to look like. Okay, this is how it's going to look like. So this is Fy, and this is also Fy. Look at this, all the stress distribution in all the fiber is same. This is Fy, but in elastic section only these two fibers were having the maximum stress, and all other fibers were having actually less strength, that of the yield stress. Okay, this is called plastic state. It's called plastic state. This is at elastic state. This is at elastic state. So now I need to calculate my capacity. Okay, so now I know the area here, right? I know the area, and this area is actually stressed to this level. So what happens here? Now here, this is actually going to be a compressive force, and this actually is going to be an tensile force, and these two are going to form at some particular distance Z. So C into Z will give me the moment capacity. That moment capacity is the plastic moment capacity. Now MP is equals to C into Z or T into Z, and also we know that for equilibrium, okay, for equilibrium C should be equals to T. So what is C? It is Fy into area of compression is equals to Fy into area of tension. So Fy get cancelled. So area of compression should be equals to area of tension. So what it tells you? It tells that like the area of compression should be equals to area of tension. Therefore, both the areas should be half of the total area. Okay. So then what? So if this has to be the same, and this neutral axis has to cut the area into two equal areas. Okay, so that is why this is also called as, in the plastic analysis, is the equal area axis. Equal area axis. Okay, so now once I got this one, what is this Z? Z is nothing but is the centered distance from the neutral axis to where the compression force is acting. Let me take it as yc dash, and it is yt dash is the central distance to t from the neutral axis or the equal area axis. So therefore my MP becomes Fy into a by 2 into yc bar plus yt bar. So this is our plastic capacity of the section. Plastic capacity of the section. So in the plastic capacity of the section, look at this. Now the strain here, it is more. This angle is called as curvature. This P is nothing but 1 by R. Okay. So at the plastic stage, it is having a very high rotation. Okay, high curvature. It's of course because we are loading beyond